Hello everyone, I'm Alison from Kiel University, and today I would like to present to you our work where we take a new 3D approach to study interseismic fault loading at strike-slip faults using InSAR time series data. Here we studied the North Anatolian fault, which is a major right lateral strike-slip fault zone in the north of Turkey. It has a history of high seismic activity. Since surface displacement corresponds to crustal deformation and therefore fault loading, we study this loading of the NRF by performing an optimization for slip deficits and locking depth along the fault. For this, we use several planar rectangular sources and a viscoelastic layered half-space medium model. And as a result, we get a first 3D model of slip rates and locking depth along the fault. Our database is a set of 12 descending and 8 ascending tracks of time series data. It was recorded by the NBSat satellite between 2002 and 2010, and it covers the entire fault except for the ascending data where there is a data gap between 35 and 38 degrees. We then proceeded to subtract plate velocity from our data tracks to simulate a backslip event, of which we then could optimize for the backslip and locking depth, whereas the backslip corresponds to the slip deficit. We calculated these velocities using an Eurasia Anatolia Euler poll published by Le Pichon and Creamer in 2010. In our optimization, the fault was represented by 28 rectangular planar source segments, for which each a locking depth and a backslip is optimized for. The fault geometry is assumed to be right lateral strike slip for all segments. Here you can see our preliminary results, where we have solutions for locking depth and slip deficit for each of the segments. We find that in the western and easternmost parts, the locking depth and slip deficits are rather low. Meanwhile, the seismic potential seems to be significantly higher in the central part of the fault. Now, the exact values of these results should be taken with caution, as in some areas they're rather uncertain, especially due to the data coverage. It is very poor in some areas, and some of the tracks are highly influenced by noise. Also, the assumed plate velocity that was calculated through the Euler poll does not represent the measured plate velocity through GPS stations very well everywhere. We also find that our model is not too sensitive for locking depths, since they often reach the given upper limit. However, the general trends of locking are very similar to previous studies, and also plausible, so the direction we take with this 3D modeling seems to be valid and of high potential. We also estimated the seismic potential per year that builds up at each segment from the slip deficits and locking depth. And if you compare these results with a collection of all major earthquakes that have happened along the fault in the observation period, we can also see that in the central part, there seems to have happened very little stress release, where there were major earthquakes in the eastern part and many more earthquakes in the western part. So as a conclusion, the model we have here is the first 3D model of the North Anatolian fault that accounts for varying slip rates and locking depth along the fault. We created this using InSAR time series data in a viscoelastic layered half-space medium model, which is also first. Our results are in overall agreement with earlier studies, and the general distribution of our seismic potential matches the seismic events in the observation period. There are still some issues that could have been improved, most of which relate to the data quality and the poor spatial coverage. Our model also does not account for potential segmentation along the depth direction, and we generally have a low sensitivity for locking depth. However, the quality of the results could greatly benefit from data with higher spatial and temporal resolution, possibly such as time series of the new Sentinel-1 mission SAR data. Thank you very much for your attention. I hope it made you curious about our work. If you want to know more, there's a QR code where you can download slides that contain additional information and more details. But if you have questions, you can also send me an email. The address is right here. Thank you very much, and I hope to hear from you. Bye.